What's going on, everybody? Got another video here for you. This is the chain rule. This is for multivariable functions. So let's get started. It says the chain rule, case 1. Suppose that z equals f of xy is a differentiable function of x and y, where x is equal to g of t and y is equal to h of t, are both differentiable functions of t. Then z is a differentiable function of t, and we have dz is equal to dt, or dz over dt is equal to the partial of f with respect to x times the derivative of x with respect to t plus the partial of f with respect to y times the derivative of y with respect to t. And we also have dz dt is the partial of z with respect to x times the derivative of x with respect to t plus the partial of z with respect to y times the derivative of y with respect to t. So, in this, they're just using, up here they're using f, okay, and down here we're using z. And see, it's just, they say up here z is equal to f. So up here they're using the f, up here they're using the z. So it's really not, it's not bad. I'll show you later on as we work through some examples. I'll show you kind of an easy way to kind of look at it where you don't necessarily have to memorize all of this. Okay. All right, so and also note that the x and the y here, they're a function of one variable. They're just a function of t. Okay, we're gonna have this down here, right here, where we have x and y are functions of more than one variable. Okay, and I'll show you the difference in that when we get there. All right, so it says if z is equal to x squared y plus 3xy squared, where x is equal to sine 2t and y is equal to cosine t, find dz dt when t is equal to 0. All right, so what I would do if I were working these problems, I would write it out before I took the derivative. So we know the derivative of z with respect to t is equal to the partial of z with respect to x times the derivative of x with respect to t plus the partial of z with respect to y times dy dt. And look, all I did was write this down right here. That's all I did. All right, so let's do that. So this is equal to the partial of z with respect to x. So that's going to be 2xy plus 3y to the fourth. Okay, that's this partial of z with respect to x. And then times the derivative of x with respect to t. So the derivative of x would be what? 2 cosine 2t plus the partial of z with respect to y. So that's going to be x squared plus 12xy cubed. Okay. That's the partial of z with respect to y, and then times the derivative of y with respect to t. So that's times negative sine t. All right. Now, what do they want to know? They want to know that, they want us to find dz dt when t equals 0. All right, so we've got to plug 0 in for t. Now, if we wanted to, you see the x's and the y's in here. We could replace those with sine 2t and cosine t if we wanted to. But we're not going to do that. So what we're going to do is we're going to take the t equals 0 and go ahead and plug it in here. So I've got x equals sine of 2 times 0, which is the sine of 0, which is 0, and y equals the cosine of 0, which equals 1. So I have x is equal to 0 and y is equal to 1. So I'm just going to replace the x's and y's with the 0 for x and the 1 for y. And then for all of these t values, I'll plug in 0. All right. So this is equal to, well, let's write down what we're finding. dz dt when t equals 0. That's going to be 2 times 0 times 1 plus 3 times 1 to the 4th. Okay, I'm just plugging in the x and the y, times 2 times cosine of 2 times 0 plus 0 squared plus 12 times 0 times 1 cubed times negative sine of 0. All right. And basically what this is going to give us here is 3. Well, I need a parenthesis there. That's going to give us 3 times 2 times 1. See, this part right here would be 3. This would be the 2 there. And then we've got the 1 here. Plus, and then this over here, this is 0 in here, times, and then this would be 0. And so we get an answer of 6. All right. So that's not bad. Not bad at all. All right. So let's work a word problem. It says the pressure P in kilopascals. The P is the pressure, volume V in liters, and temperature capital T in kelvins of a mole of an ideal gas are related by the equation PV is equal to 8.31 T. Find the rate at which the pressure is changing when the temperature is 300 Kelvin and increasing at a rate of 0.1 Kelvin per second, and the volume is 100 liters and increasing at a rate of 0.2 liters per second. All right, so let's just kind of write down what we have. We have P times V is equal to 8.31 times capital T. All right. And they tell us, let's see the information they give us. Where is it? Okay. They want to find the rate at which the pressure is changing. So that's the change in pressure. So that would be dP dt is what we're looking for. When the temperature is 300 Kelvin, so that's when T is equal to 300, and increasing at a rate of 0.1. So that means the change in temperature is equal to 0.1. And then they tell us the volume is 100 liters and increasing at a rate of 0.2 liters per second. So that's the change in volume. All right. Now, what are we looking for? We're looking for dP dt, right? dP dt. So what I want to do is I want to take this and I want to solve it for P, 8.31 times capital T over V. There's my equation. I just solved that. I solve it for P. And I want to know the change in V, the change in volume. Okay. the change in pressure. Find the rate at which the pressure is changing. So I'm looking for dP dt. So that's going to give me dP dt is equal to what? The partial of P with respect to T times the derivative of T with respect to little t, the derivative of capital T with respect to little t, plus the partial of what? Capital P with respect to what? V. And this right here should be a capital T. I don't know why I put a lowercase t. Times the derivative of what? V with respect to t. And all I did is I used this up here. That's all I did. Okay. See, I've got P equals. So I'm finding the derivative of P with respect to T. Okay. And instead of X and Y, what do I have? Capital T and capital V. Okay. All right. So let's go ahead and find that. So I've got dP dt is the derivative of P with respect to T. Okay. The derivative of P with respect to capital T. So capital T is my variable, right? That's my variable. So that's going to be 8.31 over V. Remember, T is my variable. So you could look at it as 8.31 over V times capital T. This is my variable, and the 8.31 over V is a constant. Okay? Times the derivative of capital T with respect to T. See, that they don't give me a function for capital T, do they? So I'll leave it like that. But the good thing is I know what that value is. It's 0.1. See, they give that to me. All right. Then I need what? I need the derivative of P with respect to V. Now let me show you this real quick. So this would be 8.31 T over capital V. We could look at it like that. What's the derivative of this? Well, remember, you can write it like that. Bring the V up. And then the -1 comes down in front. And so we would get negative 8.31 T over V squared. Okay. So that's going to be minus 8.31 capital T over V squared. And then times the derivative of V with respect to T. Now, let me just go ahead and give you a little tip. Whenever you have 1 over x, the derivative of that is -1 over x squared. And you could find that by doing x to the -1, doing the power rule. Okay? But 1 over x comes up quite a bit. So I would just memorize the derivative of 1 over x is -1 over x squared. Also, just think, if you have any kind of constant term over x, what's the derivative of that? Well, it's negative that constant term over, I'm over here writing outside the line, aren't I? This is equal to 0.2. I kind of lost my boundary there. But what I was getting at is 1 over x, the derivative of that you can write as that, but just memorize that the derivative of that is -1 over x squared. Okay? And just like this one here, if you have a constant term over x, c is a constant. Well, what would be the derivative of that? -c over x squared. Just memorize that. And like I said, if you forget, you could change that to c times x to the -1 and use the power rule. Okay? Just a little tip there. Sorry about writing off the edge of the screen. I don't think I did it up here any, did I? Well, I might have just a little bit right here, but anyway. And I did it over here too. I'm losing my boundaries. X equals 0, y equals 1. Sorry about that. I have to pay closer attention. All right. So now let's plug everything in. I'm going to move this over a little bit to make sure you can see it. All right. So now all we do is we plug everything in. Okay. So I've got 8.31 over 100 times 0.1. I'm just plugging the 100 in for V, the 0.1 in for the dt over dt, minus 8.31 times 300 over 100 squared times 0.2. And then when you punch all that into your calculator, you get negative 0.04155. And so the pressure, we can say the pressure is decreasing at the rate of 0.042. We'll just round it up. It's decreasing at that rate of kilopascals per second. All right. So it's not bad. That's not too bad at all. All right. So let's go up here. We've got chain rule case 2. It says, suppose that z is equal to f of x, y is a differentiable function of x and y, where x is g of st and y is h of st, or differentiable functions of s and t. Then we have the partial of z with respect to s is partial of z with respect to x times partial x with respect to y plus partial z with respect to y times partial y with respect to s. And then the partial of z with respect to t. See, notice here we got an s and we have a t. Okay. The x and the y in this case, they're functions of two variables. So if we want to find the partial with respect to t, that would be the partial of z with respect to x times the partial of x with respect to t plus partial z with respect to y plus partial y with respect to t. S and t are independent variables, x and y are intermediate variables, and z is the dependent variable. Now, one thing I want to show you here, okay, so, you can look at this and you could memorize that if you wanted to. But let me show you something. Let me show you something how you can make it easier on yourself. So our function is z, right? So z is our dependent variable. So we have the z up here, and then we have x and y as our intermediate variables, right? And then our independent variable would be s and t. Just make a little tree diagram here. So go z to x and y to s and t. All right. And so this right here would tell us the partial of z with respect to x. This would be the partial of x with respect to s. This would be the partial of x with respect to t. This would be the partial of z with respect to y. This would be the partial of y with respect to t. And this would be the partial of y with respect to s. All right. So if you come across a problem like this where you have to take the derivative, it might help you to draw this tree diagram out. And it makes it easier. And we'll draw the tree diagrams out, as we go, because I think it'll help you to find these derivatives using the chain rule. All right, so let's look at this. All right, so it says if z is equal to this, e times x times sine y. Notice, we got two variables here, where x is equal to s times t squared and y is equal to s squared times t. Find the partial of z with respect to s and the partial of z with respect to t. All right, so for this one, let's just come over here to the side and kind of sketch that tree diagram out. We've got X, Y, and then we've got the S and the T, and the S and the T. All right. So we want to find the partial of Z with respect to S. Okay. So we got to get down here to the S. You see that? We got to get down to the S here. So to do that, look, we got to go from Z to X and X to S. And we got to go from Z to Y and Y to S. So what is this? Well, this, let me change colors back. This is equal to the partial of Z, the partial of Z up here with respect to X. See that? That's going to get us from here to here. Then we've got to go from X to S. So what is this? That's the part times the partial of X with respect to S. And then plus, now we've got to do this one to get to the S. So that's going to be the partial of Z with respect to Y times the partial of what? Y with respect to S. All right. So that's not too bad, is it? And so what do we get? The partial of Z with respect to X. So we're taking the partial of this with respect to X. So that's just e to the X times sine Y times the partial of X with respect to S. So the partial of X with respect to S, that would be times T squared. Plus, now the partial of Z with respect to Y. So remember, e to the X is a constant. So that's going to be e to the X cosine Y times what? Times the partial of Y with respect to S. So the partial of Y with respect to S, that would be 2ST. And so this is going to give us T squared e to the X sine Y plus, that's going to be 2ST e to the X cosine Y. And that would be your answer for that one. All right. So now we want to do the partial of Z with respect to T. All right. So let's just kind of erase this out. And let's put those lines back in there. Now this time we've got to get to what? To T, right? The partial of Z with respect to T. So I've got to go here and then here. I've got to go here and then here. So this is going to be what? The partial of Z with respect to X times the partial of X with respect to T plus the partial of Z with respect to Y times the partial of Y with respect to T. All right. And so this is going to be the partial of Z with respect to X. So that's just going to be e to the X sine Y times what? Partial of X with respect to T. So that's going to be 2ST. And then plus the partial of Z with respect to Y. Let's see. Let me move that over. I didn't leave myself much room to work these problems, did I? All right. Partial of Z with respect to Y. That's e to the X cosine Y. And then partial Y with respect to T. So that's just times S squared. And so this is going to be 2ST e to the X sine Y plus S squared e to the X cosine Y. And then this would be your answer. All right. Plenty of room there. Plenty of room. Let's maybe move this over just a little bit more. All right, there we go. All right, so I'm telling you, this right here, drawing this tree diagram, that it really helps. Okay, It helps quite a bit. All right, let's look at this right here. We've got the chain rule, general version. Suppose that u is a differentiable function of the variables x1 to xn, and each x sub j is a differentiable function of the m variables t1 to tm. Then u is a function of t1 to tm, and the partial of u with respect to the partial of t sub I. All right, that should be an I right there. That would be the partial of u with respect to the partial of x1 times partial x1 partial t sub I. And then and it just keeps going. And that's for each I equals 1 to m. So we could just, it doesn't really matter how many variables we have. All right, so and here's an example that's going to help with this this general version here. It says write out the chain rule for the case where w is equal to this, x is equal to this, y, z, and t. Okay, so we've got a ton of variables here. Okay, so let's look at this. Let's draw out our tree diagram. So we've got our function w. That's our main function. Okay. All right, and what we're writing out the case for is the partial of w with respect to u. I'll write it right here. We're writing out the partial of w with respect to u and the partial of w with respect to v. That's what we're writing out. So let's draw our tree diagram. So there's w. That's our dependent variable, and then we have our intermediate, which would be what, x, y, z, and t. So that's going to be here. Let's see if I can draw this out halfway decent. So we've got x, y, z, and t, and then each of those have a u and a v. See that? U and a v. A u and a v. A u and a v. All right, so let's write out this derivative here. So the partial of w with respect to u. So remember, I got to go from w to u. So I go w x u, w y u, w z u, w t u. All right, so to go from w to x, that's going to be the partial of w with respect to x, and then x to u, so that's the partial of x with respect to u. All right, and then I've got to go this one, so that's going to be plus the partial of w with respect to y times the partial of y with respect to u. See, you're just following the tree branches is all you're doing. And then we've got the partial of w. Let me make that w look a little better. Partial of w with respect to z times the partial of z with respect to u. And then plus the partial of w with respect to t times the partial of t with respect to u. All right, so that would be our partial derivative. The partial derivative of w with respect to u. So why don't you pause the video right now and see if you can write the partial of w with respect to v. Okay. All right. So hopefully you actually paused the video and tried it. Well, let's write it down. That's the partial of w with respect to x times the partial of x with respect to v. We're going to x and then v. And then plus the partial of w with respect to y times the partial of y with respect to v. And then plus, that's going to be the partial of w with respect to z times the partial of z with respect to v. And then plus the partial of w with respect to t times the partial of t with respect to u. And this is what they're wanting you to find. They're just wanting to give you practice writing out the chain rule like that. Okay? All right. So let's look at, yeah, there we go. Let's look at this example. All right, it says if u is equal to x to the fourth y plus y squared times z cubed, where x equal rs times e to the t, y equals rs squared e to the negative t, z equals r squared s sine t. Find the value of partial of u with respect to s when r equals 2, s equals 1, and t equals 0. All right. So, like I said before, let's go over to the side and write down. We got our dependent variable, our intermediate variable, and then our independent variables. So we've got u. That's our. Let me do it in a little bit different color. All right. So we've got u, and then our intermediate variable. We have what? We've got a x, y, and a z. X, Y, Z, and then we have what? RST. See that? We've got RST. We've got RST. That's the variables of X, Y, and Z is R, S, and T. So let's write this out, what we're looking for. So we're looking for the partial of U with respect to S. That's what they're asking us to find. So we've got to go to each of the S values. So that's here, 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 and here. All right, so that's going to be the partial of X with, the partial of U with respect to X times the partial of X with respect to S. All right, plus the partial of u with respect to y times the partial of y with respect to s. So here we go, partial u with respect to y times partial y with respect to s, plus the partial of u with respect to z times the partial of z with respect to s. All right. All right, so let's find it. So we've got the partial of u with respect to s is the partial of u with respect to x. So that's just going to be 4x cubed, right? I'm sorry, 4x cubed y, all right, times what? Times the partial of x with respect to s. So that's the partial of this with respect to s. So remember, the r and the t variables, those are constants. So that's times r e to the t. And then that's going to be plus the partial of u with respect to y. So that's going to be x to the fourth plus 2yz cubed. All right, let me move that on over. All right. Times the partial of y with respect to s. So that means s is our variable. Everything else is a constant. So that's going to be times 2rs e to the negative t. And then that's going to be plus the partial of u with respect to z. So that's going to be 3y squared z squared times the partial of z with respect to s. So that's going to be r squared sine t. All right. So what did they want us to do? All right. So we want to find this, the partial of u with respect to s when r is equal to 2, s is equal to 1, and t is equal to 0. So we've got x is equal to what? So remember, r is 2, s is 1, and t is 0. So we're going to take each of those and we're going to figure out what x, y, and z are. I mean, I could, for the x, y, and z, I could plug all of this mess in there, but that's just going to make it look nasty. So let's just figure out what x and y are. So x would be, let's see, 2 times 1 times e to the 0, which is 2. Y is equal to 2 times 1 squared times e to the negative 0, which is 2. And then z, let me leave a little more space there. Z is equal to, was that 2 squared times 1 times sine of 0, which is 0. So now let's plug everything in. So we've got the partial of u with respect to s evaluated at t equal, we've got r equal 2, s equal 1, and t equals 0. Well, that's going to give us, let's plug everything in. So that's 4 times 2 cubed times, let's see, y is 1. No, y is 2 also. Y is 2. Times r, which is 2 times e to the t is 0, plus, and then that's going to be 2 to the 4th. Yeah, because let me underline these in red so I can find them easier. I hope I'm not plugging one in wrong. All right, so we got that, and that's going to be plus 2 times y times z cubed, so that's times 0 cubed, times 2 times r times s times e to the negative 0, plus, and then we've got 3 times 2 squared times 0 squared times, let's see, r is 2 squared times sine of 0. All right, I hope I didn't plug one in wrong. We probably need another parenthesis right there. Well, that's all jumbled up. It's tough when you're doing this all crammed up in this little old space. But anyway, whenever you punch that all into your calculator, you'll end up getting 192 as an answer. If I made a stupid, careless mistake plugging the numbers in, then I just did. I'm not going to go back and check it. You know how to plug numbers in for the variables, okay? It's all cramped up on this, screen, this little screen here. All right, so it says if g of st is equal to f of s squared minus t squared minus s squared, and f is differentiable, show that g satisfies this equation. T times the partial of g with respect to s plus s times the partial of g with respect to t equals 0. We want to show that that's true. All right, so what we could do here is we can kind of simplify this a little bit so it doesn't look so nasty. This right here, this s squared minus t squared minus s, that's f. To make it a little easier to work with, let's come up here and say let x equal s squared minus t squared and y equal t squared minus s squared. So if we do that, then g of st is equal to f of x, y. Okay? All right, so we want to find the partial of g with respect to s. So what is that going to be? Okay, what do we have here? Well, if we come up here and we let f be our dependent variable, and then we've got x and y, and then we would have s and t. All right. So I'm going based on, we've got the f of x, y, and then x is a function in terms of s and t, y is a function in terms of s and t. And so we're finding the partial of g with respect to s. And remember, I mean, you see here, g is the same thing as f. G of st is the same thing as f of xy. All right, so this is going to be the partial of f with respect to x, right, times the partial of x with respect to s, plus the partial of f with respect to y times the partial of y with respect to s. That's my partial g with respect to s. And what is that going to equal? Well, the partial of f with respect to x. What does that give me? Well, that's just partial f with respect to x times because they don't really tell us what f is, do they? They don't give us what that function actually is. So it's partial of f with respect to x times the partial of x with respect to s, so that's times 2s, plus the partial of f with respect to y times the partial of y with respect to s. So partial y with respect to s, that's negative 2s. And then we need the partial of g with respect to t. So we come over here, that's going to be the partial of f with respect to x times the partial of x with respect to t, plus the partial of f with respect to y times the partial of y with respect to t. I'm just following that tree diagram. And so that's the partial of f with respect to x times the partial of x with respect to t. And so that's going to be times negative 2t, plus the partial of f with respect to y times the partial of y with respect to t. Partial y with respect to t is 2t, and this is an f right here. All right, so we have t times the partial of g with respect to s plus s times the partial of g with respect to t is equal to t times, okay, and now I'm going to plug in the partial of g with respect to s, which is this thing right here. So that's 2s partial f with respect to x. I'm just writing the 2s first, minus 2s times the partial of f with respect to y. All right. All right, so hopefully everybody's good there. And then that is plus s times, and then that's going to be this one, negative 2t partial f with respect to x plus 2t partial f with respect to y. And you can see if I distribute the t's, the t here and the s's here, let's just go ahead and do it. So that's 2st partial f with respect to x minus 2st partial f with respect to y minus 2st partial f with respect to x plus 2st partial f with respect to y. And you can see that they're all going to cancel out, and we would get 0. And that's what they wanted us to show there. Okay. All right, let's look at another one. it says if z is equal to f of xy has a continuous second order partial derivative, and x is equal to r squared plus s squared, and y is equal to 2rs, find expressions for partial z with respect to r and the second partial of z with respect to r. All right, so let's see what we have here. All right, so let's look at the partial of z with respect to r. All right, so look, like I said, if it helps, okay, we've got z here, and then we've got x, y, rs, rs. Okay. All right, so this is going to be the partial of z with respect to x times the partial of x with respect to r plus the partial of z with respect to y times the partial of y with respect to r. And so the partial of z with respect to x, what does that equal? Well, that's the partial of z with respect to x. See, they don't tell us what the function is. They don't say z equals this. So we leave it as partial z with respect to x times the partial of x with respect to r. So that's times 2r plus the partial of z with respect to y times the partial of y with respect to r. So that's going to be times 2s. All right. So what do we have here? We have the partial of z with let's write it like this: 2r times partial z with respect to x plus 2s partial z with respect to y. So this is our answer for the first part. I'm going to circle it in red because we actually need that. Okay. All right. Now comes the fun part. We need the second partial, right? So what is the second partial? Well, the second partial of z with respect to r would equal what? The partial of this right? We've got to take the partial of this. See, this is the first partial. So then we take the partial of this. See, the partial of this with respect to r. Now, keep in mind, this is not this times this. This is the partial of this with respect to r. It would be kind of like the partial of f with respect to r. But the f here, that is this whole thing. Okay? All right. So let's see what we need to do here. All right, so if we do that, we're just taking the partial of each term. This right here is what? This is going to be the product rule. All right, so the partial, so that's the derivative of this one times this one, right? The derivative of 2r times the partial z with respect to r. With respect to x. Okay, so it's the derivative of 2r, which is 2 times the partial of z with respect to x, plus the partial of this second term here, right? I hope everybody understands that. It's the partial of this. So that's going to be the derivative of the first function times the second function plus the first function times the derivative of the second. Right? And this is the derivative of the second function. It's the partial derivative of this function with respect to r. That's all we're doing there. Plus, okay, the derivative of this first function, which would be 0 times partial z with respect to y, plus the first function times the partial of the second function. So that would be the partial with respect to r of partial z with respect to y. All right. So I hope all that makes sense. So we've got 2 times the partial of z with respect to x plus 2r partial with respect to r of partial z with respect to x plus 2s times partial with respect to r of partial z with respect to y. And that's a partial symbol there. Those are not 2's. All right, so basically all I did is I rewrote this because all that goes to 0, and I just, you leave that out. All right. All right, so now what do we need to do? All right. So what we need to do here is, so we've got this in terms of partial z with respect to x. We need to figure out what this is, and we need to figure out what this is. So let's look at that. So we're gonna come down here separately and do that. Okay. All right. So I've got the partial of r, the partial with respect to r of the partial z with respect to x. All right. So now, to do this, let's just go ahead. Let's go ahead and make our tree diagram. It's going to make it much easier for us to do this. So my dependent is what? That's going to be the partial z with respect to x. And then what do we have coming off that? X and y. And then we got r and s. R and s. There's my intermediate, and there's my independent. See, before, remember, remember the problem we work? It was like partial of w. And so the w would go here. Or if we had the partial of z, the z would go here. But we've got the partial of z with respect to x with respect to r. See, we're taking the partial of this. This would be like the partial of, say, w with respect to r. But see, the w is this thing right here. And if we were doing the partial of w, then what would we have up here? We would have the w here, right? So that's why we have the partial z with respect to x. All right. It just makes it easier. So what do we do? So what does this equal? Well, it's the partial of what? The partial of this with respect to x, right? Think about it. Look at this. Think about if this was a w here. What would that be? That would be the partial of w with respect to x. See? But the partial z with respect to x, that's our w. Okay? I don't know if this makes it better, but I mean, does it help if you see it like this? We're taking the partial of that with respect to x. I'm just leaving it written out to the side. That's all we're doing. Okay? All right. And then, so it's the partial of this with respect to x times what? The partial of x with respect to r times the partial of x with respect to r. Plus, then what? The partial of this with respect to y, right? The partial of this with respect to y times the partial of y with respect to r. See, it's not it's not really that bad, is it? It's not too bad at all. See, it helps so much to just write that out. Makes a bunch of difference. All right. And so let's see what we've got here. So we can write this as the second partial of z with respect to x, right? This right here, that's the second partial of z with respect to x, times the partial of x with respect to r. We'll come up here. The partial of x with respect to r would be 2r. So that's times 2r. Plus, and then this would be what? This would be the second partial of z with respect to y, and then with respect to x, that's this, and then times the partial of y with respect to r. Partial of y with respect to r would be 2s. So that would be times 2s. And so there's this. See, we're calculating this, and now we're going to calculate this one. See, we got that. So we're going to replace this with this. All right. So now let's find the partial of z with respect to y, and we're taking the derivative, the partial of that with respect to r. So once again, let's just come up here, okay? Come up here and let's do our tree diagram. So we got partial z with respect to y. We got x, y. We've got rs, rs. Okay? All right. So this is going to be what? We're going from here to here. Here, let me do this. Let's do it in red. There, and then there. There, and then there. All right. So we got the partial of this with respect to x. All right. So that's the partial of z with respect to y. And we're taking the partial of that with respect to x, times the partial of x with respect to r, plus the partial of z with respect to x with respect to y. Whoop. I'm sorry. I wrote that wrong, didn't I? That should be a y, not an x. All right. Times the partial of y with respect to r. All right. So hopefully that makes sense. Okay? I hope that makes sense. All right. So we've got, this is what? This would be the second partial of z with respect to x, then with respect to y, times the partial of x with respect to r. Partial of x with respect to r is 2r. Oh, where am I? That's 2r. Plus, that's the second partial of z with respect to y, times the partial of y with respect to r. Partial y with respect to r, that would be 2s. So times 2s. All right. So hopefully that all made sense to you. I hope it did. So now we have the second partial. Well, let me do this. Let's do this. We've got the second partial of z with respect to x. Isn't that what they want? No, with respect to r. See, this is what they're wanting us to find. So that's what we're finding right there. Okay. So what we can do now is, okay, we're good right there. So what we're going to do now is, you see this right here, we calculated that right there. And this right here, we calculated right here. See, we're going to take this and plug it into here and here. All right. So let's see what we have here. All right, so plugging that in, we've got, let's see, 2 times partial z with respect to x. Okay, I just wrote the first term down, plus, and that's going to be plus 2r times this. Well, what do we get here? We get the second partial z with respect to x. Well, let's write the 2r first. 2r times the second partial of z with respect to x plus 2s second partial z with respect to y, then with respect to x, plus 2s times, and then this one, so I'm going to plug this in. That's the second partial z with respect to x, then with respect to y. Whoop. Hang on. Yeah, 2s times that. Make sure I wrote all that right. Yep. All right, so that's going to be 2r second partial z with respect to x, then with respect to y, plus 2s second partial z with respect to y. All right. And then when we distribute everything, okay, let's see what happens when we distribute everything. That's going to be 2 partial z with respect to x plus, all right, so let's see what we get here. This is going to be plus 4r squared second partial z with respect to x plus, all right, now look at this. I'm going to save a step here. When I distribute that and I distribute that, I get what? 4rs. 4rs. So 4rs plus 4rs is 8rs times the second partial of z with respect to x and then with respect to y. If you remember earlier, it doesn't matter what order you do it in. The partial with respect to y and then x is the same thing as with respect to x and then y. So we can just write, I'll just write this one as the partial with respect to x and then y, and then we can combine those two. And then that's going to be plus 4s squared second partial z with respect to y. Oh, I should have a 2 right there. And so this is what they were wanting. So we've got the partial, the second partial of z with respect to r. Okay. All right. So that one was a doozy, wasn't it? But but that's the thing. It's not that bad. Or I hope by doing that one, it shows you how easy it can be. Let me see if I can find one. If you draw that, it makes it a lot easier. Okay. Remember, whatever function you're taking the partial of, that's the first one, and then you've got your intermediate variables and then your independent variables. Okay, so just write that out. All right, so let's go back and look at implicit differentiation. We're almost done. We don't have a lot left. Let's look at implicit differentiation. Suppose that an equation of the form f of x, y equals 0 defines y implicitly as a differentiable function of x. That is, y equals f of x, where f of x equals 0 for all x in the domain of f. If capital F is differentiable, then dy dx is equal to the negative partial of f, capital F, with respect to x over the partial of capital F with respect to y. All right. So what is this? This is what? This is implicit differentiation. Now, and I'm going to show you. I'm going to show you in this example. Just watch how neat this is. All right. So remember up here what it says. If you have your function capital F is equal to 0. So what we have here is we would have capital F of xy is equal to x cubed plus y cubed minus 6xy. So I'm just moving the 6xy to the other side. And then what does our formula tell us to do? We want the partial with respect to x and the partial with respect to y. We need to find both of those. So I've got the partial with respect to x. Just remember, this is just different notation. Okay, it means the same thing. That's 3x squared minus 6y. And the partial with respect to y is equal to 3y squared minus 6x. And so what are they wanting us to find? Y prime, right? So we have dy dx, remember, is negative that over that. So that's just negative 3x squared minus 6y over 3y squared minus 6x. And I can draw that y a little bit better. And there's your, well, and then that would equal what? Negative x squared minus 2y over y squared minus 2x. Because 3 goes into all of them. Reduce your fractions. Remember, you learned that in elementary school, how to reduce fractions. All right, so that's finding dy dx. Now, think about when you were taking Calc 1 and you learned implicit differentiation. Remember that? Let's just look at that. We'll take the time to do it on this one. X cubed plus y cubed equals 6xy. I'm going to go through this kind of quick, but remember, you've got what? You've got 3x squared plus 3y squared times y prime. Remember, the implicit differentiation is equal to 6y plus 6x y prime. Okay. And then this is going to give us, let's see, 3y squared y prime minus 6xy prime. Remember, we're solving for y prime now, equals 6y minus 3x squared. And I tell you, let's do this. Let's put the minus 3x squared, where is it? Plus 6y. It doesn't matter if we put the 3x squared first or last. It makes no difference. And then we get y prime is y prime times 3y squared minus 6x. I hope I haven't made a mistake. I'm going through this kind of fast. I just want to show you. And then divide both sides. Y prime is negative 3x squared plus 6y over 3y squared minus 6x. I get that? Do that. All right, and then let's factor a negative out of the top. So y prime is negative 3x squared minus 6y over 3y squared minus 6x, which is negative, and then 3 goes into everything. And see, we used that formula instead of going through all of that. Okay. All right, so that's pretty neat. All right, so let's look at this one. It says, suppose that z is given implicitly as a function z equals f of xy by an equation of the form f of xy z equals 0. This means that f of xy f of xy equals 0 for all xy in the domain of f. If big F and little f are differentiable, then the partial of z with respect to x is equal to the partial of f with respect to x over the partial of f with respect to z. And then the partial of z with respect to y is negative partial f with respect to y over partial f with respect to z. And I don't know if I said the negative for this one, but it is negative. All right, so this is implicit for multivariable calculus. All right, so we have us a function here, and they want us to find the partial with respect to x and the partial with respect to y. All right, so let's find it and see what we get. So for here, what do I have? I have f of x, y, z is equal to x cubed plus y cubed plus z cubed plus 4xyz plus 4 equals 0. Move that 4 over. And so I'm finding the partial of z with respect to x. That's the first one I'm going to find. And we know that is negative fx over fz. See, we're just using this formula right here. Well, if it makes you feel better, we can write it like this. All right. All right, so let's find fx. So we're taking the partial of this with respect to x. So that's 3x squared plus 6yz. And then we've got the partial with respect to z. That's going to be 3z squared plus 6xy. And so now we have the partial of z with respect to x is negative 3x squared plus 6yz over 3z squared plus 6xy, which is negative x squared plus 2yz over z squared plus 3 plus 2xy. All right. So this is pretty easy, right? And then we want the partial of z with respect to y, which is negative. And then we come up here to this one, partial with respect to y and over partial with respect to z. So that's the partial with respect to y over the partial with respect to z. And so we've got partial with respect to y. That is going to be 3y squared plus 6xz. And we already found partial with respect to z. We'll just write it down here again so we can at least see it when I scroll back up. All right. And so the partial of z with respect to y is equal to negative. That's 3y squared plus 6xz over 3z squared plus 6xy, which is negative y squared plus, why did I write a 6, plus 3xz over z squared plus 3xy. And there's that partial z with respect to y. And look at there, that's the end of the video. So that wasn't too bad, was it? All right. So the chain rule, it's really not that difficult. I would suggest drawing out the tree diagrams whenever you're doing them. And then, after you practice enough, you might be good enough to where you don't have to do that. And then you get up there and you do a chain rule problem on your test and you get it right, and your teacher say, man, he's good at this. He don't have to draw that tree diagram to see it. But anyway, that's the video. I hope you enjoyed it. I hope it helped. Check out my other videos. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.